Let me tell you something that nobody in the popular science world wants to admit out loud. The problem with getting to Mars is not money. It is not political will. It is not even the current state of rocket engineering. The problem is physics itself, and physics does not negotiate. Physics does not care about your ambitions or your timelines or your press releases. Physics has a set of rules baked into the structure of reality, and those rules form a wall around this planet that no amount of clever engineering has ever come close to breaking. So let me walk you through the actual machinery of why Mars is not simply difficult. It is, by the laws of nature as we currently understand them, effectively prohibited. Start with the most obvious thing: space is not empty. That sounds like a contradiction because we always call it the vacuum of space, and technically it is a vacuum, almost no gas molecules, almost no matter in the classical sense. But it is absolutely drenched in radiation, not the gentle kind of radiation you get from a hospital X-ray machine. We are talking about galactic cosmic rays, which are atomic nuclei, mostly protons and helium nuclei, that have been accelerated to a significant fraction of the speed of light by the shock waves of supernova explosions thousands of light years away. These particles carry kinetic energies that dwarf anything we can produce in a particle accelerator. A single galactic cosmic ray proton can carry as much kinetic energy as a baseball thrown at a reasonable pitch. Now shrink that baseball down to the size of a proton. All that energy packed into something 100,000 times smaller than an atom. And those things are flying through you right now, constantly, in every direction. Here on Earth you are protected from almost all of them. The Earth has a magnetic field generated by the churning of liquid iron in its outer core, and that field deflects the lower energy-charged particles before they even reach the upper atmosphere. The particles that do punch through the magnetic shield hit the thick blanket of atmosphere, about 10 meters of water-equivalent shielding sitting above your head, and they trigger cascades of secondary particles that lose their energy before reaching the ground at sea level. You are living inside a double-layer fortress, and you have never once had to think about it. Mars has neither of those layers. The Martian core cooled and solidified billions of years ago. A planetary magnetic dynamo requires a liquid, electrically conducting layer churning under differential rotation, and Mars simply lost that geological activity. Without the internal heat engine, the dynamo died. When the dynamo died, the magnetic shield evaporated. And then the solar wind, a continuous stream of charged particles blowing off the surface of the sun, spent hundreds of millions of years stripping away the Martian atmosphere, molecule by molecule. What is left is a thin wisp of carbon dioxide at roughly 1% of Earth's surface pressure. That provides essentially zero radiation shielding. Standing on the surface of Mars means standing in the full, unattenuated beam of galactic cosmic rays and solar particle events, with nothing between you and the universe. Now let us talk about what radiation actually does to a living body, because this is where the physics becomes deeply intimate with biology. Your DNA is a molecule. It is a long, twisted ladder of base pairs encoding the information your cells need to replicate and function. A fast-moving proton or heavy ion passing through your body is doing something very specific. As it passes through tissue, it is depositing energy along its track. Physicists call this linear energy transfer, and for heavy ions it is enormous. The particle is ripping electrons off molecules, ionizing them, leaving a trail of chemical wreckage through your tissue. When that track of ionization passes through the double helix of a DNA molecule, it can snap both strands simultaneously. That is a double-strand break. Your cells have repair machinery for single-strand breaks, which happen all the time from normal metabolism. But a double-strand break in both rails of the ladder simultaneously is a fundamentally harder problem. The repair machinery often makes mistakes. Those mistakes become mutations. Enough mutations in the right genes mean cancer. And in deep space, you are accumulating those breaks at a rate that makes the long-term cancer probability not a statistical risk, but a near certainty over a multi-year mission. But here is what makes galactic cosmic rays particularly vicious compared to ordinary radiation sources. They are not uniform beams. They are individual high-energy projectiles. Think of it this way. Imagine you are standing in a room and someone is shooting microscopic bullets at you from every direction, randomly, continuously. Most of them pass right through you without hitting anything critical. But a small fraction will hit something that matters. Over enough time, one will hit the lens cells in your eye and trigger a cataract. One will hit a critical tumor suppressor gene in a lung cell and plant a time bomb. One will hit a neuron in your central nervous system and kill it. You cannot predict which bullet hits which target, but you can calculate the probability distribution over time, and over a 3-year round trip to Mars, the numbers are genuinely alarming. NASA's own estimates for a Mars mission put the career radiation dose for astronauts well above the agency's own acceptable cancer risk limits, and those limits are already set higher than what any other regulated industry would permit. Now comes the shielding problem, and this is where the physics turns absolutely brutal. Your first instinct when you hear about radiation is to put metal around yourself, build a thick aluminum hull, wrap it in lead. This is the intuitive answer, and it is completely wrong, and understanding why it is wrong teaches you something profound about how particles interact with matter. When a galactic cosmic ray, especially a heavy iron nucleus moving at half the speed of light, hits a dense metal wall, it does not simply stop. It undergoes what physicists call spallation. The incoming nucleus smashes into the nuclei of the metal atoms, and the collision fragments into a spray of secondary particles, neutrons, protons, lighter nuclei, pions. You have taken one incoming high-energy projectile and converted it into a shotgun blast of secondary radiation. A thin metal wall does not reduce the radiation dose inside the ship. It can actually increase it by producing this secondary shower. Think of it as trying to stop a speeding car by putting a wall of glass in front of it. The car shatters the glass, and now you have 1,000 high-velocity shards flying in every direction. The metal hull of a conventional spacecraft acts as a radiation multiplier, not a radiation shield. The material that actually stops this kind of radiation most effectively is hydrogen-rich material. Water is the best practical option. Water contains 2 hydrogen atoms per molecule, and hydrogen, being the lightest element with no neutrons in its most common isotope, absorbs the incoming energy without producing the same catastrophic secondary cascade. The physics works because hydrogen has the same mass as a proton, and when 2 objects of equal mass collide, the energy transfer is maximized. It is like a billiard ball hitting another billiard ball head-on. The second ball takes almost all the kinetic energy, and the first ball nearly stops. That is how you actually slow down and absorb the incoming radiation. So the answer is water shielding. You need a thick layer of water around the crew compartment. How thick? Calculations suggest you need roughly 50 to 100 grams of water per square centimeter of surface area to bring the radiation dose down to something approaching acceptable levels for a long-duration mission. Let me translate that into practical numbers. A cylinder large enough to house a crew of 6 for 3 years might have a surface area of several hundred square meters. Providing 50 grams per square centimeter of water over that area means you need hundreds of thousands of kilograms of water just for the radiation shield. That is hundreds of metric tons of water that you have to lift off the surface of the Earth and accelerate to Mars transfer velocity. And this is where the rocket equation destroys everything. The Tsiolkovsky rocket equation is one of the most unforgiving mathematical truths in all of engineering. It says that the ratio of the mass you start with, the full rocket plus propellant, to the mass you end with, just the payload at your destination, is an exponential function of the velocity change you need. The equation is mass ratio equals e raised to the power of delta v divided by exhaust velocity. The velocity change needed to get from low Earth orbit to a Mars transfer trajectory is roughly 4 kilometers per second. Chemical rockets have exhaust velocities of around 4 kilometers per second. That gives you a mass ratio of roughly e to the power of 1, which is about 2.7. So you need a starting mass 2.7 times your ending mass. That means more than half your starting mass has to be propellant. Now add hundreds of metric tons of water shielding to the ship. That water is part of the payload mass. To push that water to Mars, you need propellant whose mass is a large multiple of the water. But the propellant tanks themselves have mass, and the engines needed to push all that mass have mass. You need more propellant to push the propellant. Each kilogram you add to the payload requires roughly 2 to 3 kilograms of propellant, which requires more structure to hold it, which requires more propellant to push the structure. The equation is exponential. The rocket equation does not add requirements linearly. It compounds them. The more mass you try to lift, the worse the mass fraction problem becomes, and it cascades until the architecture of the mission collapses under its own weight. Engineers call this the tyranny of the rocket equation, and it is not a problem of clever design or better materials. It is a mathematical consequence of the fact that you must carry your own reaction mass. Every kilogram of payload you want to deliver to Mars must be paid for in propellant, and that propellant itself has to be accelerated, so it needs more propellant, and so on. The universe has essentially set up a trap. To protect your crew from radiation, you need heavy water shielding. To push heavy water shielding through space, you need enormous amounts of propellant. To carry enormous amounts of propellant, you need a gigantic rocket. And a gigantic rocket with heavy propellant tanks and heavy engines requires even more propellant to lift, which makes the rocket even heavier, which collapses the mass fraction until you cannot physically get the vehicle off the ground. The largest rocket ever flown, the Saturn V that sent humans to the moon, could place about 45 metric tons into a translunar trajectory. A Mars mission with adequate water shielding might need a payload mass, an order of magnitude larger than that just for the water alone, before you count the crew cabin, life support systems, landing hardware, surface habitat, return vehicle, and food. No chemical rocket architecture can bridge that gap. Not because we have not tried hard enough, because the physics of chemical combustion, the maximum energy you can extract from breaking and forming molecular bonds, has a hard ceiling on exhaust velocity, and that ceiling is fixed by quantum chemistry. Now you might say, what about nuclear propulsion? A nuclear thermal rocket uses a fission reactor to heat propellant to much higher temperatures, which increases exhaust velocity. Exhaust velocities of 8 to 9 kilometers per second are theoretically achievable, roughly double that of chemical rockets. That sounds like a significant improvement, and it is, in terms of propellant efficiency. But even doubling the exhaust velocity only changes the exponential in the rocket equation moderately, and a nuclear reactor has its own enormous mass penalty. The reactor shielding needed to protect the crew from the reactor radiation is substantial. And you still have to deal with the galactic cosmic ray problem on top of the reactor radiation problem. You are adding complexity and mass to solve one problem, while the fundamental mass fraction mathematics still constrains the total system. And we have not even discussed solar particle events yet. These are sudden massive eruptions of energetic particles from the sun, driven by coronal mass ejections. A severe solar particle event can deliver a radiation dose that is acutely dangerous in a matter of hours, producing radiation sickness, nausea, vomiting, bone marrow suppression, and potentially death from acute radiation syndrome at high enough doses. On Earth, your magnetic field and atmosphere stop these completely. On a Mars transit ship with minimal shielding, a major solar particle event during the voyage could be a crew-killing emergency. The problem is you cannot predict them with enough warning. The light from the eruption arrives 8 minutes after the event at Earth. The particles themselves arrive anywhere from minutes to days later depending on their energy, but the highest energy particles from a fast event can arrive within 30 minutes. You need a storm shelter, a small, heavily shielded refuge inside the ship with very dense water shielding, where the crew can retreat on short notice. That storm shelter adds mass. Everything adds mass, and the rocket equation punishes every kilogram exponentially. On the Martian surface, the situation is somewhat different, but not better. You are no longer in transit, so you can use the mass of the planet itself for shielding by going underground. Several meters of Martian regolith overhead provides reasonable protection against galactic cosmic rays and completely stops solar particle events. Underground habitats carved into the Martian rock or covered in deep regolith piles are a physically viable shielding strategy for a surface base. But then you have built a permanent underground facility on a planet with no liquid water on its surface, an atmosphere you cannot breathe, no magnetic field, soil that contains perchlorates which are toxic to humans, and surface temperatures that swing from -60 to near freezing in the best equatorial zones. You are not colonizing a planet. You are occupying a bunker on an actively hostile world. The deeper issue is that Mars is not a slightly difficult version of Earth. It is a geologically dead body. The plate tectonics that recycle carbon and minerals on Earth, the magnetic dynamo that shields the biosphere, the thick nitrogen and oxygen atmosphere, the liquid water oceans that buffer temperature and drive weather and make biochemistry possible, All of these are products of the same underlying energy source. Earth is geologically active because it has a hot interior with radiogenic heat from uranium and thorium decay and residual heat from its formation, and the energy of the moon-forming impact event still slowly radiating outward. Mars is smaller, it cooled faster, the geology died, and a geologically dead planet cannot maintain a magnetic field. A planet without a magnetic field cannot hold a thick atmosphere against the relentless pressure of the solar wind. And a planet without a thick atmosphere is bathed in radiation that makes the surface chemically sterile and biologically lethal. There is a deep physics lesson here that goes beyond Mars specifically. The habitability of a planet is not a fixed, permanent property. It is the output of a dynamic system maintained by ongoing energy flows. Earth is habitable right now because it has the right combination of internal heat, orbital parameters, mass, magnetic field, and atmospheric chemistry. And these things are all connected. Pull on one thread and the whole tapestry unravels, as it did on Mars billions of years ago when the core cooled. The universe does not owe any particular planet a habitable climate. Earth got lucky in a very specific and physically quantifiable way, and the probability of finding that exact combination of factors in a second place in our solar system within traveling distance turns out to be essentially zero. So when you put it all together, you have an absolutely closed loop of physical constraints. Cosmic rays from supernova shockwaves carry kinetic energies that shred DNA. The only practical shielding is water. Adequate water shielding masses hundreds of metric tons. Moving hundreds of metric tons through interplanetary space requires propellant masses that make chemical rockets physically impossible to scale, and nuclear rockets marginally better but still straining against exponential mass fraction. Mathematics. And the destination itself is a geologically dead, magnetically unshielded, atmospherically stripped, perchlorate-contaminated vacuum desert where any long-term surface habitation requires living underground. Physics has not banned Mars exploration out of spite. It has simply constructed a set of equations and material properties that interact in ways that make the engineering costs scale far beyond what any plausible near-term technology can address. The rocket equation is not going to be repealed. The relationship between linear energy transfer and double-strand DNA breaks is not going to change. The cooling rate of a small planet's core is a fact of thermodynamics that has already run its course 4 billion years ago. What we can do, and what we likely will do, is send robotic systems. Robots do not have DNA. They do not get radiation sickness. They do not need water shielding or breathable atmosphere or protection from perchlorates. A robotic spacecraft is a much lighter, simpler system that can be adequately hardened against radiation at a small fraction of the mass penalty you would pay for a human crew. The physics is not equally hostile to all kinds of exploration. It is specifically, precisely, and almost elegantly hostile to the carbon-based, water-containing, DNA-dependent biological machines that we happen to be. And that is not a failure of ambition. That is the universe telling you exactly what it is made of, and how seriously it takes its own rules.